Okay, so it's time to start talking about continuous random variables. And to start doing that, I want to contrast discrete random variable with one that's a lot like it, but continuous. Okay, so what I've got here on the board are uniform random variables. And by uniform, I mean that the probabilities are the same, they're sort of even. Um, there's no outcome that's more likely than another one. And so for the discrete random variable, kind of what I've got in mind here is rolling a die, right? So a die can be 1, 2, 3, 4, 5, or 6. Those are the possible outcomes. And each of those happens with probability 1/6. So what I've done here is I've kind of graphed the PMF here. Okay, so this is the discrete PMF, and it's the same. It's 1/6 for x equals 1, x equals 2, all the way up to x equals 6, and it's 0 everywhere else. Okay, and that's what we've even got written right here. Okay, so let's now think about how to make that continuous. So the idea here is that now x can take any real value on this interval between 0 to 6. Okay, so it can be any of those integer values, but it could be 1.5, it could be pi, it could be the square root of 2. All these numbers, all these real numbers here are possible outcomes for random variable x, for continuous uniform random variable x. Okay. Um, what's tricky here is that we now have a set of possible outcomes that is not only infinite, but is uncountable. And I'm not going to make too much of the difference here, but it is really the uncountableness that's causing the problems. So you might remember with the Poisson random variable, that can take a potentially infinite number of values there, but we could still count them, right? Because that's what a Poisson random variable represents, is in fact a count. We can't count the real numbers. No matter how close to real numbers are, there's always something in between them, and that makes things tricky if we want to add the requirement that that the probability of the sample space has to be 1. Okay, all right. So how do we do that? I've got a graph here that you might think is kind of capturing this idea of uh, uniform probability. I've got something that's uh, equal to 1/6 over the values 0 to 6. Here it's flat and it's 0 everywhere else. And this is not exactly a PMF. We would call this probability density function, okay, or PDF. That's what we call it. So for discrete random variables, it's a probability mass function. And the way the logic behind those names is that we have probability mass assigned to individual points. Here's the critical thing with continuous random variables. I'll sort of write essentially the same point two different ways, but they're both a little bit on the trippy side. Okay, one is if I can write, I will write that one, we do not assign probabilities to individual outcomes for continuous random variables. Okay, and I might as well just write the second part of this, get all the weird stuff over at once. The second thing is the value of the probability density function at some value x, let's call it x star, is not the probability that x equals x star. Okay, so again, this is for continuous random variable. And we kind of know it's a continuous random variable because we're talking about a probability density function as opposed to a probability mass function. Okay. So let me just emphasize the point. It could be a little bit hard to wrap your brain around. We're not assigning some probability to like x equals 3 or something like that. Those are undefined. What we can do is we assign probabilities to ranges of outcomes. Okay. Probabilities are assigned to intervals. Okay. And the probability that x is between values a and b is the area under the PDF between a and b. Okay, so we can't assign a probability to a single point. We can't say, oh, let's think about x equals 3 and look at the height of this thing that's sort of like a probability mass function. You might sort of think that that would give us the probability, but no, we can't do that because we're not assigning probabilities to individual events. Rather, we can assign probabilities to intervals. So we could, if we wanted to, we could assign probability to the interval 2.99 to 3.01 and calculate that probability. I'm going to calculate a slightly bigger probability because I want one that I can draw here. And I think I'll go ahead and go to the next page for that. Okay, so let's say I want the probability that x is between 3 and 5 here. Okay. And what I'm saying, I just wrote it on the other board there, that the probability that x is between 3 and 5 is just this area under the PDF. And I can just calculate with that with geometry, right? Area is, it's a rectangle, so the area is base times height. So the base of that rectangle is 2, 5 minus 3, and the height is 1/6, I'm asserting here. And that equals 1/3, and that's what I'm saying, that is our probability. Okay, so with continuous random variables, the probabilities are always assigned to intervals, and we find that probability by looking at the area under the PDF for the interval whose probabilities we want. All right. The one last point I'll make here, and then I think we'll go on to the next lesson. How did I know that this the PDF was equal to 1/6 here? So if I wanted to write out the PDF as a function, I would just say that the function is equal to the constant value 1/6 on this interval between 0 and 6. And the other thing I might write if I was actually going to be careful about it is I'll write the whole thing here, that the PDF is 1/6 for just copying x between 0 and 6, and 0, sometimes people abbreviate it otherwise, everywhere else. Okay? And so we indeed do see that this function is 0, 0, 0, it's 0 all along here. It's just on this one interval where it's got the flat top there. How did I know that the height of that interval had to be 1/6? I use the fact that continuous random variables, just like discrete random variables, have to obey the Kolmogorov axioms. Okay, so this is what we need for the probability of the sample space to be 1. Okay, remember that from the very beginning of the class? What that means for a continuous random variable is that the total area under the whole PDF has to equal 1, has to integrate to 1. That area has to be 1. And if the base of the rectangle here is 6, what do we need for the height to get it to equal 1? We need for the height to be 1/6. Okay. All right. So that kind of covers the really weird stuff about continuous random variables, this fact that we can't assign probabilities to individual outcomes. And the reason why we can't assign probabilities to individual outcomes is because they are uncountable. So this problem of just trying to add up the probabilities assigned to outcomes, we would never get to 1. But we can find functions where the area under the function is 1. And those are the functions that we can use for the PDFs of continuous random variables. Okay, so there'll be more to say about this, and I'll see you in the next lesson for that.